Hello and welcome. Today we are going to be demonstrating a spinning top in MOMDYN version 1.1, which is going to use a couple of the new features in the recent app update, notably the spherical joint and the general rigid body. So we'll watch this a few times, tinker around with the views, and this is of course a fairly classic problem in dynamics. And I'm going to show you that it's made exceedingly easy to create this model using the MOMDYN application. So I'm going to give it a name. We're going to just call this spinning top. And a description, which is a demo of the spherical joint and general rigid body. All right, we're going to put this in a uniform gravity field with a gravitational constant of 9.8 meters per second squared in the direction minus y, and extend the time duration to 10 seconds and set the tolerance small so that we get a nice smooth animation. And we'll go ahead and start here from our blank slate. So the first thing that we're going to do is create our spherical joint. So going into the edit menu, hit the plus sign next to spherical. So commonly in a spinning top model, it would be a ZXZ or a 313 rotation. The way that is handled in MOMDYN is to use quaternions for the back-end simulation. And so in that sense, the rotation sequence doesn't necessarily matter, but we'll use ZXZ just for commonality with the common definition of a spinning top model. Hit the check mark. That'll create our joint so we can see this new frame that was just created. And then the next thing I'm going to do is offset the center of gravity for our spinning top. So I'm going to go to not the spherical joint, but the prismatic joint. In the A reference frame, which was created by that joint, I'm going to create a constant valued offset with a value of 1. Oh, I don't need emojis. So that created that vector in the point B. And now I'm simply going to go add our new general rigid body. So here's the help text for that body, in case anyone is interested. But the main point here is rather than a box or a cone or a cylinder that has a fixed inertial value related to the geometry, you can go in and give it any moment of inertia and mass that you want. So I mentioned this is a spinning top. This is going to be the heaviest spinning top that you've ever seen. So I'm going to give it a mass of 60 kilograms, IXX 50 kilograms times meters squared, IYY 40, and IZZ 30. Hit OK, and what we see here is on our main screen, we now have this diamond or kite-shaped form. That's an arbitrary graphic that we create for the general rigid body. It's generally shaped in a way that in a hypothetical sense, you could create a body that had the same inertial properties as you defined in the general sense, that had the same diamond or kite shape. So I didn't give any motion or any initial rate to the spherical joint that we defined. So we can see initially this pretty much just acts like a pendulum, swinging back and forth and rotating about that A sub Z axis. So that's not terribly interesting, but what we actually want to demonstrate here in our joints menu is that if we add an initial rate to this spherical joint, or an initial rotation about the top axis, that it'll actually tend to stabilize. So what we're going to do is go into this rate R naught, which will be the rate about the local x-axis of the joint or of the frame named A, associated with also the joint named A, and we're going to start this body rotating. And we're going to see some different motion of the body when we give that initial rotation. So 5 or 5 radians per second is not especially large, but we can see rather than falling down like a pendulum, it starts to precess around that J-axis. So it's not totally stable. It doesn't tend to make itself upright, but you can see rather than just falling like a pendulum, it rotates around. So now, that was with a relatively small initial velocity or initial angular velocity about the a sub x axis. If we make this large, so if we triple the rate r naught to 15, now what we should expect to see is that the body will itself tend to stabilize. Quick comment about the equations of motion. We can see here on the report tab, the mass matrix, we can see the inertial tensor there, which also contains the mass of the body with the offset difference xb. And similarly, we see in the forcing that term shows up. And also the gravitational force there, which is multiplied by a component of the quaternion. So if we hit check again, now with the higher angular rate, we should expect, rather than the body kind of falling, it will actually tend to stabilize itself. So sure enough, we can see the precession, but it tends to stay just about at the initial angle that we defined at the beginning. And to give a little bit more insight, we can see the plot of the states. At the top, the oscillations there, those are actually the quaternion states. So they kind of look like distorted sine waves, if you will. And then at the bottom, because this is largely a stable body, you can see the primary axis of rotation in blue there, which is the omega x. It's pretty much constant. We see some oscillation in the two off-axis terms on the bottom. So that is it. As you can see, this is a fairly complex dynamical simulation that we created just in a couple minutes and derived our equations of motion and gave ourselves nice, insightful plots. I hope this will be a useful tool for anybody that's learning dynamics, and I'll leave it there. So thank you very much for watching, and enjoy your weekend.